Hi, good morning. My name is Lauren Regani. I'm a media officer with the National Research Council. I'd like to welcome you all for coming and those who are joining on the web to the release of a new National Research Council report, Abrupt Impacts of Climate Change, Anticipating Surprises. So at today's event, we'll hear from three of our committee members, the chair, Jim White, Tony Barnosky, and remotely from Richard Alley at Penn State. After their brief remarks, we'll do a moderated question and answer session. Those of you in the room, there's a mic on the floor, and please state your name and affiliation when asking a question. And those on the web can submit questions to climatechange@nas.edu. Climate change, all one word. And please follow the conversation or tweet if you're in the room using the hashtag AbruptChange. And now I'll turn it over to your moderator for the day, Amanda Stout, who is the director of the Board on Atmospheric Sciences and Climate.
Thank you. Thanks, Lauren. Good morning, everybody, and welcome. I'm just really excited to see how much interest there is in this report, both here in the room and those of you joining online. So thank you so much for joining us. We are very excited today to release this report, Abrupt Impacts of Climate Change, Anticipating Surprises. And I think this report is a really excellent example of the type of independent and objective advice that the National Research Council can provide on issues of relevance to our nation. And certainly we can't argue that climate change and the potential for abrupt climate change is of great interest to our nation. This report, like all of our reports, is authored by a group of volunteers, some of the top science and scientists in the nation, and we are really thankful for the work that they put into this and grateful that three of our committee members on this project are able to join us today. So first we're going to hear from Jim White, who's a professor at the University of Colorado in Boulder. And then we'll hear from Tony Barnosky. As you heard, he's at University of California in Berkeley. And then we're delighted that Richard Alley is able to join us via WebEx. And so he's at Penn State and will join us as well. So with that, I'm going to turn it over to Jim, who's going to give a little overview of the report.
Thank you so much, Amanda. And I thank you all for coming today. Today we are releasing a report that we've been working on for about the last year and a half on abrupt climate change. You might ask why. The reality is the climate is changing. It is changing in ways that challenge us to adapt, both economically and socially. And those most challenging aspects of climate change are the abrupt ones, the features of the climate system that can happen and happen rapidly. So it's important to recognize that not only does climate change itself, but that there are impacts on human systems and on natural ecosystems. And the report looked, as Tony will elaborate on, looked not only at those rapid changes in the climate system itself, like changes in temperature, precipitation, something like that, but also looked at the fact that a slowly changing system can push other parts of the system past thresholds. Perhaps the easiest one to understand is the height of the stair steps in the New York City subway system. A storm surge that does not breach that is a problem, but it's not a huge problem. Another 3 inches and boom, you have a huge mess, as we saw with Superstorm Sandy. So next slide. Our climate system is capable of some remarkable changes. This is a plot of the temperature record from Greenland ice core. In the northern hemisphere, we see very large swings in temperature. You see in the red line there. It's important to recognize that those changes are on the order of 10 degrees to 15 degrees Celsius. You see the scale there. To scale that for you, it's like going from Miami to Montreal in a climate sense. And this happens in far less than a human lifetime. Some of these changes in some of the ice cores happen in a matter of a few years, less time than it takes to get through college, which at the University of Colorado is probably 5-6 years, unfortunately, as in most universities. The important point is that our climate system has these thresholds. Fortunately, we've not seen anything this large recently, and the report does not call out that there will be anything this large coming in our future. However, the fact that thresholds do exist is an important feature of our climate system is an important point for all of us to recognize. So next slide. So the report was tasked with several key questions. One was to assess our current knowledge about abrupt climate changes, and you'll see in the report a table that lists the abrupt climate changes of interest in the next 100 years. So we looked at that time frame. We also, very importantly, call for an abrupt climate change early warning system that I'll come back and elaborate on in a few minutes. But it's important to keep that in mind because I started this out by saying climate change is real and it's happening. And one of the features that we saw when we looked back at previous reports was that time after time there had been recommendations that we need to act. We need to do something about climate change. In order to be adaptive, in order to be resilient to climate change, we need to do something. And that's the key message of this report, that indeed the time has come for us to quit talking and actually take some action. And finally, we also looked at the scientific understanding and our monitoring capabilities. It's key for us to understand that today, while we monitor many parts of our environment, many parts of our own environment, say banks, and there's cameras on dashboards of police cars. There's cameras everywhere, but they watch us. And remarkably, very few of those watching devices are pointed at the environment, which is our most important and most economically important and precious asset that we have. It provides us with food, it provides us with clean water, it provides us with a livable climate. We ought to be watching that system with the kind of equal zeal that we watch banks and other places where we keep our most precious things. So with that, I will turn this over to Tony.
And I will also add my welcome and thank you all for coming. I just want to say a few words about what we really mean by abrupt change. And basically, we're talking about things that happen within a few years to a decade or so. That is things that young people, and hopefully most of us in this room, will be around to see. So it's a very short time frame. We do discuss some longer frame issues, but by abrupt climate change, we're really worried about what's going to happen in the next several years to decades. When we talk about abrupt changes, we're also using that terminology in a very specific way to think about a change from how things are now to a new normal. And in the scientific jargon, that's a state change. It's a lot like watching water boil for your tea. Nothing seems to happen at first. The water gets hotter, it eventually hits a threshold, a boiling point, and then you notice it. So that's a state change. That's the sort of thing we're thinking about on a much larger scale. Now, as far as the climate system goes, there are two ways that manifests. One is a change in the actual physical climate system. That is things like a rapid shift in where ocean currents are located or where the jet stream is. That would rearrange weather patterns pretty much all over Earth. The other kind of abrupt change is in systems that climate influences. Excuse me. And for that, it doesn't take an abrupt climate change. It can be a gradual climate change, a gradual rise in temperature, for example, that hits a threshold at which, for example, areas that now are great corn producers will no longer be able to produce corn. So a gradual change that results in a threshold effect. Another example of that would be rising ocean acidity that affects the development of corals and other species and causes widespread extinctions, as I'll point out in a minute. Okay, next please. So we, in fact, already notice some of these abrupt changes taking place. If we track, and this is one of the best examples, if we track how much ice is covering the Arctic in the late summer, we find that since the late 1970s, there's been a very dramatic decrease. And that has actually been a much faster decrease in ice coverage than we would have anticipated. This opening up the water that time of year has effects on the whole climate system in that the air-water interface is different than an air-ice interface. It also affects human systems, and I believe we could go to the next slide. It now looks like shipping lanes are going to be opening up. That's going to become a very economically and politically interesting issue as we shorten those traverse times for ocean liners. But it's still the Arctic. You still need certain kinds of ships to get through there, and there's a long lead time to build up to that. So this change is happening essentially faster than we can build the ships to take advantage of it. There are also major impacts on the natural world. In the case of this Arctic example, by opening up that water and thinning the ice, you allow more sunlight to get to the lower parts of the water. More algae grows, changes the food chain from the bottom up. Likewise, we lose some of the top members of the food chain, things like walruses, polar bears, large marine mammals. So we're changing it from the top down. So very dramatic changes as a result of this. Next, please. And in fact, those changes in natural systems emerged as some of the most plausibly worrying changes we might witness in the next several years. What's happening is the planet is going to be warmer than most species living on Earth today have seen it, including humans, by the year 2070. The pace of change that takes us there is actually orders of magnitude higher than what species have experienced in past tens of millions of years. As a result, habitats are shifting and changing in ways that species just can't adapt to fast enough or can't move fast enough. So the things that are on the horizon under business as usual scenarios are, for example, by 30, 40 years from now, dramatic reduction in coral reef ecosystems. That holds about 10% of the world's fisheries and about 25% of all the fish known in the sea in terms of numbers of species. These are big changes. The organisms that live at the tops of mountaintops are already starting to get pushed upwards towards their limits and are at peril. And some of the hardest hit areas on land are going to be the tropics and subtropics, which hold about 2/3 of all the land plants and animal species in the world. So these are big things we might expect to see under business as usual scenarios. Now, not all of the changes that we considered and looked at are as worrisome in the short term as these two I just mentioned. And at this point, I think I'll turn it over to Richard to explain some of those things to you.
Thank you, Tony, and I thank all of you for your good humor. I'm sorry I'm not there with you. When this is over, I'm going to run down to class, and I will be seeing student presentations on subjects related to this. So it will be a fascinating thing, but they have a call on me. So at any rate, I hope you're looking at a piece of the good news. There is good news in the world. When we had first really understood that during the Ice Age there were these very large, abrupt, widespread climate changes that were linked to the North Atlantic, clearly until the hard science had been done, we didn't know whether one of these was in our near future. And through serious monitoring, serious modeling, we now have good confidence that while we are pushing in the direction that will change the North Atlantic, well, the North Atlantic is highly likely to change, and those changes really are likely to affect people and fisheries and other things, and knowing about them can be valuable. It's very unlikely that that's going to happen rapidly. So this is more of over decades and a century rather than this year or next year. And the science has worked very well on this. The first discovery of what we didn't know, the scientific statements gave the broad range of possibilities, then get in, measure, monitor, model, and we know that this is less likely. And so that's a good thing. Another one that's sort of good news is that we do know there is a very large amount of methane in the seafloor, frozen in clathrates and in bubbles underneath those clathrates. There's a very large amount of carbon frozen in Arctic soils. If we warm it up, we have fairly high confidence that this will start to melt some of the methane ices. It will change Arctic soils in a way that in the long term will put methane and CO2 into the atmosphere. Whatever we do to the climate by warming it, nature is likely to amplify and make it an even bigger change. But when we first discovered this, there were worries about the possibility of giant methane belches changing the world almost instantly. And the good science has been done, and now we have fairly high confidence that there are safety valves, and as a consequence, giant methane belches are not the big worry. It's more of a slow feedback. And so there really have been things that have been learned. In doing the science showing that the abrupt impact is unlikely, we have learned that knowing about these, continuing to study them, can give us knowledge that will be helpful, because these really are systems that will affect us in the future, but they don't look like they're going to jump really fast. However, there are still cases that we're not sure whether there will be a fast jump, and probably the biggest of those is the one you see in red there, the West Antarctic ice sheet. We have high confidence. If you warm the air, you warm the water, it tends to melt ice. Warming is going to melt mountain glaciers. Warming will melt pieces of Greenland. Too much warming will make Greenland unsustainable. But melting Greenland and mountain glaciers from above is a moderately slow process. And for Greenland, at least, to melt the whole thing and raise sea level 23 feet would take centuries, not decades. We do know that ice sheets can dump icebergs into the ocean where they raise the sea level, and then they can go find someplace warm to melt. That process is not so limited in speed, and so where ice sheets can dump icebergs rapidly, they can cause faster sea level rise. There are speed limiters in Greenland. The ice flows through narrow fjords, and friction with the sides tends to hold the speed back a little bit. Pieces of Greenland, pieces of East Antarctica, and especially West Antarctica have the potential to have very little speed limitation. And so there are sort of really bad dream scenarios for West Antarctica that still could cause very rapid sea level rise that we just don't have well quantified yet. We have not yet had the time to do the measuring, the monitoring, the modeling, and to get it right to tell you whether there's a real chance of West Antarctica dumping. That's a place where more research would really be helpful. Virtually regardless of whether it's fast or not, we know that Greenland, Antarctica, mountain glaciers can contribute sea level rise, which can force our built systems over thresholds. And very clearly, the difference between water going over the levee into New Orleans versus staying just below the top of the levee, or going into the subways versus staying out of the subways in New York, is huge. And regardless of how fast the change is, those things will matter. Okay. We were asking the committee to look at another number of other abrupt climate changes or possibilities of abrupt climate changes, and so there's a whole lot of things assessed that you'll see on the next slide. These include issues such as growth of dead zones. Are we going to see lack of oxygen in the ocean? If there's just enough oxygen, the fish can be happy. If the oxygen drops below where the fish can live, they get very unhappy. That's an abrupt threshold that can be reached. And so there's a great number of issues that you will find more words on the state of the knowledge in there. But there certainly are things that even though the danger of a North Atlantic shutdown does not appear to be imminent, there are a number of other systems that it would be really nice to know about. And as you move from physical systems through ecosystems into economies, you get more and more chances for places where thresholds are going to be reached. Okay, what we really care about is what this means for humans, and we have these systems, we have these thresholds. The changes in the Arctic are likely to have huge impacts, but they're going to move into conditions where we can be happy. If we build for them, they will open some opportunities like shipping or exploration for valuable things. A lot of our food now is grown at temperatures that are higher than those food crops like, and we're pushing towards unexperienced warmth in the tropics if we keep burning, things that haven't happened in a very long time. And so probably the biggest issues are going to show up in the warm places, even though it will be much easier to see them and we will meet them quicker in the Arctic. And so with that, I will pass it back to Jim, and he can tell you a little more about how one might move forward on this.
Thank you so much, Richard. Richard did mention there was a slide that he has that you guys didn't see, but there is a list of potential abrupt changes that we ranked in terms of high concern, intermediate concern, and low concern in the report itself, and you'll find that table in a couple of locations. I think probably, to me, the two biggest take-home messages in this report are that, as I said earlier, it's not just about climate, it's about how climate pushes other systems past thresholds, and that's very important for everyone to understand that, for example, a very small increase in temperature above a certain threshold can push crops from being able to be grown in an area, say corn being able to grow in an area, to not being grown in an area. And those kind of thresholds exist in ecosystems, and we need to recognize those. The other main take-home point is, I believe, the call for an abrupt change early warning system. So what we're talking about here is really a climate change early warning system, but we know that those parts that can change rapidly are those parts we need to focus on. And so we're calling for an abrupt climate early warning system. How that system is built, how it's developed, is only laid out in bare bones in the report. We know that there needs to be a monitoring capability. We know that we need to be watching the planet. As I pointed out, we watch our streets, we watch our banks, we watch, if you live in the UK, they watch everything. We watch other parts of the system very well, and we do not watch our environment nearly with the same amount of care and zeal. So it has to start with monitoring. We have to model, we have to take those results and feed them into models. And then that has to be put together in a synthesis that these things have to feed back on each other. And probably most importantly, and this is where you'll find that this particular committee reached its point of expertise, and we need to pass this off. That information needs to be fed into social science models of how you communicate these kind of issues. A good example of that would be the hurricane warning system, where I think we've all seen that cone of potential where the hurricane's going to strike shrink as time goes by. That's physical science, learning about how hurricanes work and how they track winds and how to actually track hurricanes. We shrink that. But also at the same time, we've learned more about how to communicate. We've learned that when to say you've got to get out of here, and when not to say you've got to get out of here. And yes, we still make mistakes, but we've learned a lot about how to communicate that in an effective way to the public. Those models exist, that research exists, that science exists, and that really needs to be put together with the physical science. I think probably another good example of this that I'll throw out now, and we can talk about it later, is groundwater. In our country, we put up a couple of satellites, gravity measuring satellites, that as it turns out, the biggest reason why gravity changes below our feet here in continental regions is how much water is in the ground below us. And so for a decade, we've been able to monitor groundwater either increasing or decreasing throughout the world. And across most of the United States, groundwater is decreasing. And in the southeast, decreasing very rapidly. This is an area that receives more than 40 inches of rain per year. We don't think about drought in Atlanta. We don't think about drought in Alabama. But indeed, as groundwater supplies shrink, that's important information. Agriculture depends on groundwater to get through droughts. And having an early warning system that can take that information from gravity satellites, maybe improve it, probably could do a whole lot better in terms of that information. But taking that information, feeding it into the right kind of models, and then feeding it into existing systems by which we communicate with the agricultural community, express them. Maybe it's time we back off on groundwater. Maybe we move to a different cropping. Maybe we use more drought-resistant crops. That's the kind of information that we can use proactively and in a way that would make our food supplies, in this case, more resilient. There are many other examples of this. We have trillions of dollars of assets along the coast that we haven't even begun to catalog in terms of even a foot rise in sea level, which is quite well known is going to happen, much less the kind of 3 feet level that we think is quite probable by the end of this century. So I think with that, I will stop here. And I believe, Amanda, you going to take over from here?
Mm-hmm.
All right.
Actually, I can invite you both up.
Yeah.
So thanks again to our speakers and our committee members here. Now we're going to have a little bit of time for Q&A. And so if folks in the room have questions, there's a microphone here. Feel free to line up and we'll take those. And then
I have a couple questions from the web, so if you don't mind me taking some initiative and kicking things off while people collect their thoughts. For any of the panelists, this comes from Seth Bornstein at the AP. Do you consider abrupt climate change more of a threat than the continuous, more gradual impacts? And how would more monitoring help? What aren't we doing already, and what specifically could we see with new specific types of monitoring that we don't see now?
I'll start off and then turn it over to Jim. Yes, I would say definitely the way we have looked at abrupt climate change, it represents a shift in how to think about the problem, and it does make it look a lot more serious than gradual change through time. When you think about gradual changes, you can kind of see where the road is and know where you're going. When you think about abrupt changes and threshold effects, the road suddenly drops out from under you. And it's those kinds of things that we're suggesting we need to anticipate in a much more comprehensive way in order to avoid surprises that are going to cause society pain. Jim?
What was the second part of that question?
The second part was what specific, how would more monitoring help, and what specifically could we see with what specific types of monitoring that we don't see now?
Okay. First, to choose between gradual climate change and abrupt climate change doesn't sound like a very good choice to me. If there was a third option, I would take it. But I agree with Tony that parts of the system that change quite rapidly and force us into a force us into a reactive as opposed to a proactive mode are those that I think are most concerning. How monitoring helps is, I think that's fairly apparent. The more we study the environment, the more we understand first how we interact with the environment. We need to recognize that we utilize most of the fresh water available to us. We grow crops on most of the farmable land that's available to us. We are already, climate change is happening at a time when we've already pushed the ability of the planet to support us in terms of clean water, food, clean air, all the ecosystem services that Tony can tell you about in great detail. We've already pushed that pretty close to the limit. And so think of this as rather than a glass that's half full, and say a 10% change in water is not going to be any difference, not going to overspill. If the glass is 90% full, and then you have, or say 95% full, and you have that same 10% change, then you can spill over. That's what we're seeing today. We're reaching that limit. So the more that we monitor, the more that we look at the planet, the more we understand about the planet, the more resilient we will be, the more capable we can be to handle changes, not only when they occur, but before they occur. And that's really what an early warning system is designed to do, to give us time. In the groundwater example, we could have time to deal with that problem rather than reach a point where it's too expensive for farmers to take water out of the ground in the southeast because it's, either the water's not there or the pumping costs are too high. We can avoid that sort of thing. We are smart creatures. We are capable of doing that.
Yeah, this is Richard. If I could chime in for a second. If you were running a bank, you definitely want to know what assets you have. You want to know what liabilities you have. And you stress test a bank to find out where the vulnerabilities are and how you're going to deal with them. And somebody keeping track of a bank really does this. Monitoring, in some sense, is finding out what are our assets and liabilities in our bank of nature, our bank of humanity, our built environment, our natural environment, to know what really is there, and then to do the thinking and the stress testing to find out where are our vulnerabilities and how can we reduce those so that we can handle stresses when they come.
Yeah. I think that's a good point, this idea that we don't even know what some of our assets are that are vulnerable. And we don't have the integration between the various systems to link the information about the climate system with our understanding of those vulnerabilities. So, all right, we have a question here in the room.
Hi, Mark Krexler with the Climatographers. And I'm approaching this from the standpoint of risk. And how does this report change how we think about the risk of climate change? From the presentation, one takeaway, particularly if you're in the business sector and you're reading about this, one takeaway is that we should be less concerned about climate risk today than we were before this report, because you've said that a lot of the big sort of abrupt change issues that are in the blogosphere being talked about are now, we can now say, oh, well, they're not going to happen for at least 100 years. Is it your intent to suggest that we should be less concerned about climate risk today than yesterday?
No, I think the intent is just the opposite, that we should be more serious about those climate risks and be prepared to do something about them. Science gives and science takes away. In this case, as Richard pointed out, the good news is that some of the features of the system that we thought were abrupt trigger points are less concerning as abrupt trigger points. They are still very concerning as long-term climate changes. But the report then also points out that there are a number of trigger points in the system that we haven't been talking about. The Western Arctic ice sheet is a good example of that. Sea level rising 3 feet in a century, it's hard to get people to get excited about that. But say it increased by a factor of 3 in the pace of change, which is quite doable and has been seen in the climate record many, many times. So an increase of 3 to 5 is not unusual in terms of sea level rise rate compared to today. Sea level rising, say, 3 feet in 30 years is a big difference. And I think we can all see that. A mortgage, you buy a beach house, and by the time you're done paying it off, it isn't worth anything anymore. That's not the intent you had when you bought that beach house. Or you build a sewage treatment plant that's intended to last for 50 years, and it doesn't. And the taxpayers are on the hook for quite a bit of money because we have to build another one further at a higher level because the system doesn't work the way it was intended to because of sea level rise. So that's, our report, I think, makes a very strong statement that it is time to take a hard look at where the assets are, what's vulnerable. Catalog those, do some thinking, do some triage, and then take serious steps about what to protect and how to protect it. And that includes both adaptation and mitigation. There's some features of this you simply can't adapt to very well, and so mitigation makes a whole lot more sense. The Western Arctic ice sheet being one of those.
Hey, Richard, you have a nice analogy about this, if you wanted to jump in.
This is Richard. If I could jump in, yes. The scholarship is very clear that if climate change arises slowly and gradually, we see it coming, we deal with it and adapt to it as it comes, that we actually still are better off economically dealing with it, that there really is a social cost of emitting carbon now, and that actions taken to reduce that and to deal with the impacts make us better off. Analogy, suppose you're a commuter. You probably took the metro to get there, but suppose you actually had to drive across Washington to get to the thing today. You probably got stuck in traffic, and you expect traffic. The best thing you can hope for if you drive across Washington is no traffic. But you might really get stuck in traffic, and while you're stuck in traffic, you might be run over by a drunk driver and killed. And so in a risk management sense, there's sort of what you expect is some problems, and it could be a little better, a little worse, or a lot worse. You can think of abrupt climate change as the drunk drivers of the Earth system. And we know that if we get the most likely outcome, dealing with it still makes us better off, just as dealing with traffic actually can make you better off. But in our transportation system, we put a lot of our effort into the drunk drivers. We have police out there trying to stop drunk drivers. We have cars with crumple zones, anti-lock brakes, airbags, child seats, mothers against drunk drivers, engineers working on better roads so we don't get killed. You know, we really work on something we don't expect to happen, because if it does, it's so consequential. And then we work on traffic as well, dealing with climate change and abrupt climate change in a risk management sense. If you take your cues from the way we deal with other things in our system, there's probably a lesson there.
All right, we have a question here in the room.
From National Public Radio. If I could ask two questions, one of which is, could you give a specific example of things we are not monitoring right now that we should be monitoring? That's question one. And question two is, by definition, if you're talking about abrupt things, you're talking about surprises. And do you have any sense of whether there are the surprises that could happen are things that you're actually will be on your radar screen, things you can anticipate, or will they just be, bolts from the blue kind of thing? How do you, obviously there's much harder kinds of surprises to deal with, but I wonder if you guys wrestled with that issue.
Sure. And I'll answer that from the perspective of ecological changes in natural capital. We definitely identified some very major risks there. I mentioned coral reefs. I mentioned the impact on tropical ecosystems. We looked at impacts to some extent on croplands. But the basic story is this, that even if we keep going on this gradual trajectory of change, even at sort of mid to high level emission scenarios, we can expect threshold effects to decrease biodiversity in all of those systems within the next few decades. Now, why do we care about that? If you actually tally up the dollar value of what we get from those natural systems in terms of things they give back to us both directly in terms of food, sustenance, water, and indirectly things like going to national parks and so on, you are talking about something on a worldwide basis that is twice the value of the entire gross world product. So that's just the pure economics of it. There's also the sort of, I guess, moral and ethical view of it that if we actually did see the magnitude of extinction that is entirely plausible with the sorts of changes we're talking about, we're looking at an extinction event on Earth that hasn't been seen since the dinosaurs went extinct. 3 out of every 4 species that we care about. So, these are big things. And those are the sorts of effects that, in fact, are very much underappreciated. And getting back to your question earlier on, are we saying that we should be less worried about climate change today than we were yesterday? That answer is definitely no. We need to be very cognizant that there are these hidden dangers out there that we haven't been thinking about that we should have been. And I've forgotten the second part of your question.
Out of the blue.
I'll give you 2 examples of things that we're not monitoring well. One is, as Richard pointed out very well, the West Antarctic ice sheet is a concern. We don't know that much about how these marine-based ice sheets, these ice sheets where the base of the ice sheet is hundreds, if not thousands of feet below sea level. We don't know how unstable they are, how rapidly they can raise sea level. We should be measuring ocean temperatures near the ice sheet. We should be measuring far better where the outlets are, where the glaciers go into the ocean. We don't do that. And that's an area of observation where we are largely blind, but we know we ought to be watching. Another area is the simple monitoring of greenhouse gases in the atmosphere. We have only 3 or 4 sites in the Arctic that watch, for example, for increases in methane that we know are likely to happen as permafrost begins to melt. We have only a handful of sites to look at that. And since 2007, NOAA's monitoring network, the primary global monitoring network, has been cut by 30%. So we are in a situation where and there was just recently an article in Proceedings of National Academy that pointed out that there was much more methane being released in continental United States than we thought. We're not watching closely enough. Now, your second part of your question is, are these things going to be complete surprises or not? Now, as a scientist, my hope is that we can study the planet well enough, monitor it well enough, understand it well enough, that we're not going to be blindsided. As a realist, I'm pretty sure we're going to be blindsided. But hopefully, the number of blindsides are small relative to the number of times in which we can use these monitoring systems to great effect and to benefit of society.
All right. Lauren, you had a question from the web?
We do, and we're getting many questions from the web, and that's great. We'll try to get to as many as we can. This one comes from Julia Cole. She's a professor of geosciences and atmospheric sciences at the University of Arizona. And she asks, what does your panel say about the role of climate model projections in anticipating abrupt change? Can the current generation of models simulate abrupt changes in the physical climate system or the potential of thresholds in physical and biological systems? How do we know whether models are good at this?
I'll start with, hi, Julie. We discussed models fairly extensively in the report. And models, I'd say, are in their early years of being able to effectively describe the abrupt climate changes of the kind we're talking about. In some cases, pretty well. In some cases, much less well. There definitely needs to be more investment in modeling. We talked about investment in monitoring, but investment in modeling is also very important, because how we take those observations and translate them into actionable predictions for how things are going to change is absolutely critical. And while we're getting better and better at this, it's quite clear that we have a ways to go.
We have a question here in the room.
I'm a reporter with ClimateWire. Regarding the early warning system, you mentioned that you kind of sketched it out in the report, but who do you think at this point is best poised to set up such a system and implement it?
Sort of in our simple way of looking at this, there are a number of excellent federal agencies, NOAA, NASA, NSF, Geological Survey among them, who already monitor quite a bit of what's going on our planet. We envisioned that getting that group together and having them talk about how to coordinate their efforts and how to build a system that would, I wouldn't say be an umbrella, but some kind of coordinated approach to this. We don't need to reinvent the wheel to do this. We need to take the spokes we already have, the hub we already have, maybe put a new tire on this thing, make it run faster, oil it up, and very importantly, merge those observations with those social science models I was talking about how to most effectively translate a potential change into a warning. That needs to happen.
Yeah, and just to add to that slightly, there's a lot of information being gathered. Not all of the information that we would like to see is, of course, but there's a lot of information out there, but it's different kinds of information in different places. And even where the same kinds of information is being collected, it's often being collected in different ways that don't exactly match up. So I think one of the key things is a standardization of what we collect, designed that in such a way that it is usable for the purposes needed for this early warning system.
All right, let's take another question from the web.
This one comes from Teresa Morad. Sorry if I butchered your name. She's the Director of Education and Diversity Programs at the Ecological Society of America. And she asks, is there a practical way to prepare for those abrupt impacts of climate change? And at what scale? Local, ecosystem, bioregional? And can we truly anticipate those surprise impacts?
Maybe Richard wants to take a crack at that one.
Sure. Still with us, Richard?
That one's a very tough one to get to. I mean, and a lot of it is because of the things in your realm. So in the physical climate system, I think we're getting better at mapping out what is going on, where it's going on, what the processes are. I would never say that we'll get all of the surprises nailed down, but I expect that most of them will be nailed down. But as we get better and better in the physical climate, I think we're gaining greater and greater respect for all of the thresholds that are in ecological systems, in economic systems, social systems, that where we really are likely to see threshold events is stability of ecosystems, is stability of economies, is at what point does a food price spike in a society combine with all the other things in the society to trigger an Arab Spring, and what is the role of climate change in that? What is the role of your ecosystem is having troubles, you're losing ecosystem services, your crop fails at the same time, you have no fallback, and you look across the border and start heading that way, and there's a border between you and resources. So I think that the real issues, we would love in physical sciences to have more funding and to keep doing more research, but I think ultimately you're going to find that the ecological, the economic, the social systems are where the real action is. Tony has more insight than I do.
Yeah, I think that's exactly right. I mean, you know what? One of the big issues is food and water, right? So the ability to look down the road 10 years and say climate is changing in such a way that we're going to have more extreme heat days in Kansas in July and August than we do now, and to somehow put some reasonable bounds on that. You can then relate that to, well, how many of those extreme heat days does corn really withstand without the crop crashing, or the same sort of logic applied to water. And if you have that information, then you can actually begin to do things like say, well, maybe we should be growing something differently, or maybe we should be using a different strain of corn that we have yet to develop. And the spin-up time on developing a new crop is not overnight. It's a decade or so. So these are the sorts of practical applications.
Mm-hmm.
I'll give you an economic example. A couple of months ago, I received a phone call from someone who builds computer systems, who builds air conditioning systems for large computer systems. I think we all know that computers generate large amounts of heat, and large server farms have to have very large air conditioning systems. He called up and asked a very simple question. He said, what's going to be the maximum temperature in 30 years? And I thought about it a second. I said, well, why do you want to know? And he said, because when we design these systems, we design them for maximum temperatures. And if I design a system that is going to be obsolete in 15 years, but the computer company is amortizing it over 30 years, this is a major economic problem. And we're beginning to see those mismatches. As Richard was saying, and as Tony was saying, we see those mismatches in ecosystems. We now begin to see them in our economic systems as well. And they will become more and more apparent as time goes by, but this happens to be one that caused me to shake my head and smile at the same time.
Well, it gets back to this idea of how we're defining abrupt changes, as those changes that are happening more quickly than this decision lifetime that you're considering. So, all right, we have another question here in the room.
Good morning. I'm Bill Brockhouse, a volunteer for the Climate Reality Project. And I just had a question. James Hansen's group came out today with a new report, which kind of lends some more urgency to the whole question of climate change. They were saying that we need to limit warming to 1 degree. And in the past, I think we've heard 2 degrees from the IPCC, and I think the World Bank last year chose 4 degrees as a disastrous level of climate change. And I just wondered, what is your, I mean, how urgent is it to, according to Hansen, we've already blown through our carbon budget, and we have to take, serious measures immediately to stay at this, within this 1 degree. They use some like paleoclimatology analysis to determine that. I just wondered if you had any comment on that.
Yeah, I mean, so definitely the key issue is how fast and to what extent are we actually going to change climate. And there's no doubt that what we really want to do is keep that upper boundary and the pace of change low and slow, okay? Because the more climate change we see, the more likelihood of these abrupt sort of surprises that we've been talking about. So there's no doubt that the bottom line issue is reducing our greenhouse gas emissions to a level that certainly does not get us past 2 degrees. That's an arguable value, but even to do that, we're talking about a 5.1% per year reduction for the next 38 years. And that's a big task. It's doable, it's technologically doable, but it's something that, in fact, we need to start today, because every year we wait to start pushes us closer to those abrupt events that we've been talking about with this report.
If I could chime in from the phone. We have high confidence and there was a recent report from the U.S. government on this, that there is a social cost of carbon, that every time we release CO2 to the air, we are costing society money. But we also have confidence that as the temperature goes up, the cost goes up faster. Each degree of warming costs more than the previous degree. And so the first one is not all that expensive, the second one more, the third one more than the second one, the fourth one more than the third one. And so I think the analogy may be that dealing with it is a little bit like saving for retirement. All delay is costly, but it helps whenever you start.
Jim?
Just briefly, Jim's making a point that the level of CO2 in the atmosphere is already far out of bounds for the last million years, as a matter of fact. And we make this point in the report as well, that you need to go back to 3 to 5 million years ago to find a time when we had roughly this amount of CO2 in the atmosphere. And the climate was much warmer, and sea level was 20 meters higher. We have a figure in the report that shows what 20 meters of sea level looks like. It's no more Delaware, which is, that makes, I always like to say, that makes sea level rise easy to understand, because Delaware was the first state in and be the first state out. If you can remember FIFO, you can remember climate change. But indeed, low and slow, as Tony said, that's the way to go. Low and slow is the way to go when it comes to climate change.
All right, we have a question from the web.
This one comes from Josh Ring, who's at the Nichols School in Buffalo, New York. Why is sudden methane release no longer considered a trigger point for abrupt climate change? And what was the science that led to this conclusion?
Mm-hmm.
I can take that, and Richard, if you want to chime in as well. So there are 2 stockpiles of carbon that we worry about when we talk about methane as an abrupt climate change. One is the carbon that's locked up in soils, which isn't methane right now, it's organic carbon. But as bugs chew on it, and as naturally the way it decays, it forms lakes on the surface, and that can actually help to form anaerobic environments that produce methane. We know from just studying the basic physics of these systems that it takes a while to melt permafrost. So while there's enough carbon locked up in permafrost alone to roughly equal coal, oil, and natural gas, and there's no reason to think that it will not come out as climate warms up, it will not come out abruptly. And I think a very important point that we make in the report is that there's a distinction between abrupt change and these low and slow kind of changes. You're still going to have to adapt to all that carbon coming out if we don't keep the temperature down. But we have had concerns in the past that this could come out abruptly. The other stockpile is the methane hydrates that Richard talked about in the presentation. And we know both from studying the physics of how these things decay and also from looking at the paleoclimate record. There's maybe one episode, maybe two episodes in the Earth's history over the last tens of millions of years where one can point a finger towards methane clathrate, or methane being released from clathrates. And so that tells us that the probability of this happening is very small. Now, again, I would caution everyone, that doesn't mean that eventually as you warm the planet up, this stuff's not going to come out. It just doesn't come out as one big belch that, as Richard pointed out, eats the world.
Richard, did you have anything to add?
Nope, beautifully stated. There is a lot of science behind this on sort of what the safety valves are and where the timescales come from, but it's high scientific confidence that this is an amplifier. What we do, this makes it more costly, but that it doesn't happen in years. It starts in years and happens over decades and centuries.
All right, we have a question here in the room.
Bruce Parker, I'm a volunteer with the Citizens Climate Lobby. So to follow up an earlier question on temperature increases, do y'all look at the threshold temperature increases that might result in abrupt climate change? In other words, down the road, even though we might not get it in the next 50 years, but if temperature were to go up another degree or 2 or 3, that somewhere down the next couple hundred years, abrupt climate change would be almost certainly to happen. And also on the going slowly on low on increase in the temperature and such. 20 feet of sea level rise would be absolutely disastrous, I would imagine. And did you all look at what the threshold would be? I mean, how much sea level rise can we tolerate before it could be decided that would really be an abrupt climate change? We probably couldn't tolerate more than 5 or 10 feet. And then when such thing likely to happen?
Well, let me tackle the first one, and then hopefully we'll probably have to ask you what you said at first. But the pace of sea level rise is what's critical here, how fast this happens. As I was pointing out, 3 feet in 100 years, there's high likelihood that we could adapt to that. Now, 3 feet of sea level rise alone means that a city like Miami, which is barely 3 feet above sea level as is, and is made up of, is not made up, but its feet are in sand and coral that you cannot defend by dikes, and that's a city that would be largely dysfunctional at that time because none of the underground systems are going to be working under that scenario. As I pointed out earlier, if you had 3 feet of sea level, if the pace of sea level rise was such that 3 feet could happen in 30 years, that's a time frame that I think would be far more shocking, and folks in a city like Miami would consider that majorly abrupt. In 30 years, I got to figure out how to move a city or move millions of people. Whereas over 100 years, it's still a very difficult situation for the people in those cities, and for all the people that are going to be impacted by as Miamians move out. But it's really a question of pace. So yes, we thought about what was at stake with a foot of sea level rise. What we found out pretty quickly was that, with the exception of places that have been clobbered, like New York City, they now know. They've brought in a whole bunch of reinsurance corporations to tell them, this is what you've got at stake along the coastlines. For the most part, we don't know the monetary value of the assets that we have lined up along the coast. We do know that coastal counties produce about 40% of our GDP. We do know there are trillions of dollars of assets. But what we call for in this report is a far more systematic approach to saying, all right, with a foot of sea level rise and the concomitant storm surges you get, what's at risk here? So with that kind of information, I think we can establish far better policy, or at least we'll have the information to establish far better policy. I forgot the first part of your question.
First part was, if you look at what point is abrupt climate change going to be very, very likely? Increase the temperature another degree or 2. Are we headed to, if not this century, next century, some abrupt climate change?
Yeah, I mean, I think that we are, in fact, already experiencing abrupt climate change, and abrupt impacts of climate change is probably a better way to put that. I mean, if you look at fire frequencies in the American West, for example, just make a simple graph that shows you what was the average number of fires per year before 1988 and what was the average number after 1988, what you see is a dramatic stair step, okay? So we're already at that new normal. As we continue to warm into the very near future, next couple of decades, we're probably going to see another one of those stair steps. So those sorts of abrupt changes are on the horizon with very high confidence, I would say. The sorts of things that are much further off in the future are things like changing the AMOC circulation. That takes a lot more forcing and a lot more time to react to that forcing. So it sort of depends on the impact you're thinking about and what's actually driving that impact in the climate system. But the short story is we're already seeing abrupt impacts, and we're going to see more.
The report also calls out, for example, the decrease in sea ice, that Arctic sea ice that Tony talked about earlier. That's an abrupt change. It's happening right before our eyes. It's happening right underneath our feet. These things are happening now, and our reaction to this now is, we stick a finger in that hole in the dike, and we stick a finger in that hole in the dike, and now we got to take our shoes off, and a couple of holes in there, and at some point we run out of things to stick into the dike. If we had predictive capability, we could borrow you and you and you and say, we need more fingers over here, and these are where the holes are likely to occur. That's what we're really calling for.
But at some point you can no longer adapt, and it's going to be really bad.
At some point, yeah, we're going to get wet.
Okay. We have time for just one quick last question. This has been such a great discussion.
My name is Richard Adams, and I study at UDC. I wanted to ask you, you think in the future we be able to create a better emergency system for like generic air masses like tornadoes, because this country here suffers from the most tornadoes in the world. We can't see them. Sometimes they're visible until they creep up on you. You think maybe in the future we'd be able to develop a better warning system for the people? Because
I certainly hope so, and I think that research is developing. Research is pushing in that direction. There are a lot of very smart people out there trying to understand tornadoes and gain predictive capability. What you've given us here is a very good example of an early warning system that already exists. It's young. It's still got a ways to go, but there's every expectation in the world that we can increase that time from maybe an hour or minutes of warning to much more, the 2 hours that would be really helpful for people to be able to get to shelter, to get out of harm's way. Imagine that mapped on a larger climate early warning system. That kind of benefit is the kind of benefit we're talking about. Thank you for your question.
that was a great way to end it. And I wanted to thank all our speakers and committee members. I know Lauren has a few remarks, but I also wanted to acknowledge the staff who worked really hard on this report, in particular Ed Dunley, who's the study director. And there's a whole bunch of other folks in the room who have been really instrumental in making this happen. So if we could do a round of applause for everybody.
I'd like to echo my thanks for the committee members for your time and effort. Again, they serve as volunteers, so we really appreciate that. We did have a lot of questions on the web that we didn't get to today, and if you give us a little bit more of your patience, we will try to respond in writing if we can. Those asking on the web, if reports are available, yes, go to www.nationalacademies.org. And the report and all related resources should be readily available to you. And for the people in the room, there are copies of the report on the table, along with our other climate change resources from the academies. And I would like to also thank Koshland Science Museum for letting us use this beautiful space. And now we invite you actually to enjoy the space. There is an interactive climate exhibit, among others. So interact with that and with each other. And again, thank you all for coming today.